If I say numbers, what comes to your mind? Probably the first answer and the most automatic will be mathematics. There are numbers everywhere, and it is difficult to say how numbers were born. Their origin is rooted in prehistory. They certainly did not appear suddenly, and they are not someone's discovery or invention. Mathematics is something that has been with us from the beginning of school until we started working. Mathematics can be found in the simplest forms: 1 plus 1, Roman numerals, the way we count, or splitting the bill among friends. So, what makes math so fun and adventurous when it comes to certain topics? We can find it in places we never expect. I'm sure this all look familiar, but did you know that these all have interesting histories? So let's explore more about numbers and patterns, their history, and how visible they are in our everyday lives.
Let's start with the tally mark system. I know most of you know this type of number system because we had done this once in our lives. It is the simplest way of assigning symbols to quantity, but becomes limited when expressing large numbers and is commonly used in settings where objects are counted per item. Where can we use this type of number system? It is commonly used in scoring or by simply doing inventories. Next is the Roman numeration system. It originated in ancient Rome and was used to measure quantity throughout the Roman Empire and is still being used today. These letters are used to represent a number. Here is a sample chart of the Roman numerals. Now you might be wondering, how did IV become 4? When a smaller value is placed before a larger one, we subtract instead of adding. So, IV means 5 minus 1. When it is VI, we are adding 5 plus 1, which is 6. So, VI means 6. Same with IX, or 9. This rule also applies with large numbers. Now, have you heard of the Egyptian numeration system? Maybe some of you did not know that it even existed. Well, the Egyptian numeration system was used in ancient Egypt at around 3000 BC. It uses symbols that symbolize the power of 10 in numbers. The symbols were called hieroglyphs. Here is a sample picture of the symbols. Numerals were formed by combining the symbols that represent the powers of 10. For example, remember that any symbol used to represent a number is a numeral, not a number. A value of a number is the sum of the values of the numerals. An example of this is shown in this video. Another numeration system is the Babylonian numeration system. It started when the Babylonians inherited the sexagesimal system, or the base 60 system, from either the Sumerian or the Ebelite civilization. These were written in cuneiform, and instead of using 60 different symbols, the Babylonians instead had 2 symbols to represent a unit value and the tens value, which they then repeated to express 60 distinct digits in their sexagesimal system. Next is the Chinese numeration system. It dated back to the 2nd century BC or earlier. The Chinese used small bamboo rods to represent the numbers from 1 to 9. The bamboo rods were then placed from right to left to represent units, tens, hundreds, thousands, and so on. Lastly, the Hindu-Arabic decimal numeration system. This is the numeration system we use nowadays in our math classes or any classes that involve computation. It originated and was propagated by Hindu mathematicians in the 6th or 7th century. The symbols 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0, called the decimal digits, are used to form the decimal numbers.
Types of numbers. We are going to take a look at the different groups of numbers that exist. Natural numbers. Natural numbers, or the counting numbers, are probably the first type of numbers you will ever have to come across. The natural numbers are whole numbers greater than 0. These numbers are 1, 2, 3, 4, and so on. These are numbers that you can physically count. The natural numbers do not include negative values. Integers. Integers are whole numbers, both negative and positive, including 0. These numbers are -3, -2, -1, 0, 1, 2, 3, and so on. Positive integers are integers greater than 0, and negative integers, not surprisingly, are integers less than 0. Rational numbers. Rational numbers are numbers that can be written as a fraction where both the numerator and denominator are integers. This means that both the top and the bottom of the fraction are whole numbers. An example of this would be 1/3, or 23/7. Irrational numbers. Irrational numbers are numbers that can't be written as fractions. Example of these are the ones such as pi and square root of 2. If we try to write these numbers as decimals, they go on forever with no recurring digits. Square numbers. Square numbers are integers that can be written as the square of some other integers. An example, a product of an integer multiplied by itself. Example of these are 4, which is 2 by 2, and 81, which is 9 by 9. Square numbers can also be written in the form of 5 squared. Then this notation means 5 squared, which is 25. Surds. Surds are numbers that are left in the form of square root of n, where n is a positive integer that is not a square number. Prime numbers. Prime numbers are greater than 1 that can only be divided by themselves, and 1 to give an integer answer. Example of these are 2, 3, 5, 7, 11, 13, 17, and so on. Note that the 2 is the first and only even prime number. Real numbers. Real numbers are all the numbers that you have ever come across, all of the rational and irrational numbers. All of these real numbers can be written in a finite or infinite decimal form, such as the most famous one, which is pi, 3.14159265 and so on.
Number pattern is a pattern or a sequence in a series of numbers. This pattern generally establishes a common relationship between all numbers. An example of this is: what is the next number in the sequence? 1, 3, 7, 13, and 21. If you notice, the answer is 31. The pattern here is that you add 2, 4, 6, 8, 10, etc. But there are different types of number patterns in math, so let's take a quick look over them. Ready? Let's start. Arithmetic sequence. This involves a sequence of numbers to which the same amount has been added or subtracted. The amount that is added or subtracted is known as common difference. Geometric sequence. This is a list of numbers that are multiplied or divided by the same amount. The amount by which the numbers are multiplied is the common ratio. Triangular numbers. Numbers in a sequence are often referred to as terms. The terms of a triangular sequence are related to the number of dots needed to create a triangle. An example of this, starting with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. The triangular sequence goes 1, 3, 6, 10, 15. You have 1 on top, then 2 at the bottom. The next row has 3, the row after has 4, and the row after has 5 dots, a total of 15 dots. Square numbers is a sequence wherein the same terms are the squares of their position in a sequence. It begins in 1, 4, 9, 16, and 25. These are the squares of the whole numbers. So for example, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9. That is why we got the sequence like that. Cube numbers. This is a sequence wherein the terms are the cubes of their position. It begins with 1, 8, 27, 64, and 125. Same mechanic as we did on the square numbers, but this time the cube of the counting numbers. So for example, 1 times 1 times 1 is 1, 2 times 2 times 2 is 8, 3 times 3 times 3 is 27. So you just continue to follow the sequence up until you reach the desired number.
Topic 4. Fibonacci numbers. Leonardo Fibonacci was from Pisa. He lived in the 13th century in Italy and is credited with discovering a mathematical sequence that's now named after him, the Fibonacci sequence. Starting at 0 and 1, this sequence is created as the sum of two preceding numbers in the sequence. So for example, 0, 1, 1, 2, 3, 5, 8, 13, 21, and 34, and so on. Surprisingly, you can find the Fibonacci sequence in a lot of things, mathematics being one of those things. But did you know, you can find it in arts and science? When talking about the Fibonacci sequence, once you visualize each number as a square, increasing in size in the same way as the sequence, and connect the opposite corners of each square, you create the Fibonacci spiral. The Fibonacci sequence is directly connected to the golden ratio, which are two quantities whose ratio is the same as the sum of the total to the longer ratio. The golden ratio is called the divine ratio. Most artists recognize the Fibonacci spiral as an expression of an aesthetically pleasing principle, which is the rule of thirds. This is used in the creation of pictures because it creates a balance in the features of the image by thirds, instead of strictly centering them, which creates more pleasing flow to the picture. Human anatomy and animals. Fibonacci is also present in human and animal anatomy, since it's related with the golden ratio. How is it present? Simply by looking at the measurements of the body parts. Body parts have measurements that make up its entire appearance, and these measurements make up the golden ratio. For example, the bones in our hands, which consist of 4 bones that connect to our wrists. It has exact measurements to make the whole hand. Plants. You can find the Fibonacci sequence in this when it comes to the growth of the actual plants. An example is the number of petals. Buttercups have 5 petals. Lilies and iris have 3 petals. Delphiniums 8 petals. Corn marigolds 13 petals, and so on. Growing points is another example that show the Fibonacci sequence. Below is a picture of those two examples.
Mathematically speaking, we say an object is symmetric if it is invariant to any various transformation. More specific, it means that however you want to transform the object, it will always be similar to its original version. If we want to be very rigorous, we can say a mathematical object is symmetric with respect to a given mathematical operation if, when applied to the object, this operation preserves some property of the object. For mathematics, maintaining the same property after some sort of operation is key to understanding many advanced concepts. Let's look at the symmetries of some finite shapes. Shapes that do not extend forever in any direction, but are confined to a bounded region of the plane. This shape has one line or axis of reflectional symmetry. It has symmetry of type D1. This shape has 3 axes of reflectional symmetry. It has a 120-degree angle of rotational symmetry. By performing this rotation again, we have a 240-degree angle of symmetry. Now let's look at the symmetries of border patterns. These are patterns in which a basic motif repeats itself indefinitely in a single direction, as in an architectural frieze, a ribbon, or the bordering design of a ceramic pot. An infinite strip with a repeating pattern is called a frieze pattern, or sometimes a border pattern, or an infinite strip pattern. The term frieze is from architecture, where a frieze refers to a decorative carving or pattern that runs horizontally just below a roofline or ceiling. Here are some examples of a frieze pattern. Since the patterns repeat, we show only a finite portion, but you should keep in mind that these pictures should extend indefinitely far in both directions. All frieze patterns have translational symmetry. A horizontal frieze pattern looks the same when slid to the left or right, and a vertical frieze pattern looks the same when slid up or down. And in general, any frieze pattern looks the same when slid along the line it is laid out upon. Again, it is both important that the patterns extend indefinitely far in both directions so that there are no ends that appear different. You can slide or translate this pattern by the basic translation shown above. This translation is the smallest translation possible. All others are multiples of this one, to the right and to the left. So this border pattern only has translational symmetry. Translational symmetry occurs in many man-made objects like bricks, wallpapers, and quilts. The pattern displays a new kind of symmetry. It has the translational symmetry common to all frieze patterns. However, the symmetry between the left footprints and the right footprints does not come from translational, nor is it due to a reflection since the prints are not next to each other. Instead, a combination of translational and reflectional is needed. This combination is called Galide reflection symmetry.
Mathematics lives and develops in a universe of its own. The effectiveness of mathematics, therefore, would derive from the fact that the universe itself would not have been written in this language. It is a language as it is capable of clarifying the mechanisms that guide the dynamics of the natural world. Here are some other facts about numbers. Did you know that 0 is the only number that can be represented in Roman numerals? There are a total of 0 zeros in Roman numerals. While the ancient Greeks were aware of 0 as a concept, they did not consider 0 to be a number at all. For example, Aristotle decided 0 wasn't a number because you couldn't divide by 0. Instead of a Roman numeral, the Latin word nulla would have been used to represent the concept of 0. The reason no numeral existed for 0 is because there was no need for a numeral to represent it. 7 is considered to be a lucky number. 7 is the most significant number across religions and cultures. For example, there are 7 colors in the rainbow, 7 days in a week, 7 notes on a musical scale, 7 seas, and 7 continents. Finally, 7 often appeared throughout the world's favorite fictional works, such as Snow White and the Seven Dwarfs, and of course, James Bond 007. 100 doesn't mean 100. The word 100 is actually derived from the Old Norse word hundredth, which actually means 120, not 100. More specifically, hundredth in Old Norse means long hundred, which equals 120 due to the duodecimal system. But good luck trying to argue that your $100 bill is worth 20% more than it is. Daily life would be totally different without numbers, and without them, all those objects, the result of scientific and technical research that surround us, would not exist. There are numbers on pages of a book, telephone numbers, license plate numbers, and numbers on a class register. Numbers are used in counting or in playing hide and seek, how much money you have in your pocket, to inform about the lunchtime, the date, the house number of a home, the speed at which a car travels, the duration of the day, or even the price of a commodity. Numbers are part of our life, of idioms, of religion, of play, of books and comics, even if perhaps we don't consider them too much.